20.2. What are the major water pollution problems in streams and lakes? Okay, so natural cleansing of rivers. Rivers can cleanse themselves of biodegradable pollutants if they are not overloaded. And second, water flow is not reduced via drought, dams, or diversions. Okay, so number one, both of these are not plausible, right? If they're not overloaded. Of course they're overloaded. Currently, 45% of the population lives on or near the coast, and that's not just in the U.S., that's worldwide. 45%. By 2025, they say it's going to be about 80% of people will live on or near the coast. So obviously, almost every waterway in the world is overloaded. So that's not going to happen. Second one, water flow is not reduced via drought, dams, or diversions. Well, California has been in a 5-6 year drought. The Ogallala Aquifer is 30 meters lower than should be. We have drought conditions in many different states, in many different places around the world. Almost every single major river across the world has been dammed at some place, so obviously that's not happening either. So what does that mean? Our rivers are not cleansing themselves of biodegradable waste, and that is true. Dilution. There used to be a saying that was, the solution to pollution is dilution. Okay, especially with rivers which flow out to the ocean, and in the ocean, just dumping straight into the ocean itself. The ocean is so big and so massive, how could we have an impact at all if we dump our waste into there, right? It's just going to float away and disperse and dilute. It'll be no problem at all. And now we're realizing, as all this crap is coming back to us, that we were in fact very, very wrong. Biodegradation is the breakdown of organic waste by bacteria. One of the most important things to remember is that as this bacteria is breaking down the waste, okay, it is sucking oxygen out of the water, right? So this is what causes these zones called hypoxia, right? You don't necessarily need to memorize that term for an FRQ, but that just means a zone of low oxygen, sometimes called dead zones, right? So if there is, so that's if there is oxygen present, right? And that's that usually takes place somewhere near the surface, or the first few meters where there is plenty of oxygen. The farther down you go, especially in a lake when it gets really, really cold, or in the ocean when it gets cold, you get to a point where there is no oxygen in the water, right? In that water column. Get down low enough, no water. So, and when the anaerobic bacteria then start breaking down biodegradable waste, they produce methane, okay? So, remember, methane at the bottom, and they're sucking out oxygen at the top, okay? And then they produce carbon dioxide. So the oxygen users, aerobic bacteria, use oxygen, produce carbon dioxide. The anaerobic bacteria, they produce methane. Which brings us to the oxygen sag curve. So we have a point source pollution with biodegradable waste, okay? As soon as the waste comes into the water, okay, this says right here, biological oxygen demand, the demand for that oxygen increases because all those bacteria start feasting on it, okay? And therefore the supply, the amount of dissolved oxygen starts to go down, okay? And the farther you move down the river, right, the more diluted it gets. Also, the farther you move down the river, the more the bacteria are working on it, right? So you finally start to dilute and get rid of this biodegradable waste to a point where the demand starts to go down. Therefore, the dissolved oxygen starts to go back up. So the farther you move downstream from this point source pollution, this point source biodegradable waste, the more you recover till eventually you reach normal conditions again. Okay. Now, also in this area, all this bacteria are feeding. All right. There's billions of bacteria, and in this process, just like when your body's breaking down food, you produce heat. So this bacteria is producing heat. So in this section of the stream, just downstream of the point source pollution, there's also an increase in thermal energy, right? And thermal energy also aids in this oxygen sag curve because oxygen doesn't like to stay dissolved in a warm liquid. Think about your Coke. If you take a Coke, two of them, right? You open one up and set it on the counter. You open a second one up and put it in the fridge. Come back 3 hours later, the one on the counter will probably be flat. It will have lost all of its carbon dioxide gas. The one in the fridge will still be bubbly because the colder the water is, or the solution, right, the better it can hold on to dissolved gases. The warmer it is, the less able it is to hold on to dissolved gases, and the gases therefore escape. Right? So the warmer it is due to the biodegradation of the bacteria, the less oxygen it can hold, so it escapes from that because it's too warm, and because the bacteria are feeding on it. So anything that goes into there, fish, other organisms, they die due to lack of oxygen, hypoxia. Water pollution challenges. Okay, so let's see. Developed countries, we have the means and power and money to enact laws and regulate different pollution. Since the 70s, laws have reduced point source pollutions quite a bit in developed countries. In developing, they do not have the funding or the government know-how to be able to do this, and as a result, half of the world's 500 biggest rivers are heavily polluted. Developing countries discharge 80 to 90% of their sewage directly into the rivers, right? Not any type of treatment, no septic tanks, just directly into the rivers. Let's see what else I wanted to say here on this one. Okay. The Cuyahoga River in the United States, going to developed countries, by 1969 it had caught on fire 13 times, which is crazy. Finally, there were some new laws enacted, which we'll get to in a little bit, that helped put the kibosh to that. Developing countries. 1/3 of China's rivers are so polluted they can't even use it for agricultural purposes. 1.3 billion Chinese live without any form of sewage treatment. 1.3 billion. Wow, that's crazy. That's almost their entire population. And then 300 million do not have access to drinkable water. All right, drinkable water by our standards, and that is almost the entire population of the United States. 300 million Chinese. We have 319 million here in the U.S. So China has almost the population of the U.S. Without clean drinking water. Lakes are vulnerable to pollution, right? Because they're not a stream or river. They don't move quickly. They're not having their water exchanged very quickly. And because they don't have water flowing in and flowing out, you end up having stagnated water, so it forms layers based on heat, right? And you get these striations. Once that happens, when you have these striations that develop, the two different temperatures of water hit each other, and they don't want to mix because of that vast temperature difference, right? Because of that lack of mixing, then we're not having this dilution taking place, so you get areas of concentrated toxins, and we get this biomagnification that takes place. The small little organisms eat only so much of this toxic material throughout their life, but if you're a top predator in the lake and you eat all the small ones that have a little bit, well, then you are magnifying those toxins through the food chain into your system, right? What's going to be more toxic? The one shrimp that is eating a little bit of toxins its entire life, or the fish that eats 15 shrimp a day, right? So the fish that eats 15 shrimp a day is going to be much more toxic than the one shrimp. Alright, so nutrients in the water. Cultural eutrophication is the pollution that is put out or put into the waterways by a society based on their habits. Farms, feedlots, urban runoff, yard runoff, mining wastes. So all of these things, all these runoffs that are high in nitrogen and high in phosphate, they're fertilizers. The algae get this in the water. It's just like putting nitrogen and phosphate on a plant, a tomato plant. It's going to help it grow. So it causes these algae blooms to occur. Now the algae, all right, it does two things. One, it forms a mat at the top, and it blocks any sunlight from reaching the plants at the bottom. The plants at the bottom, right, then they die. And once they die, they're no longer photosynthetic, and a byproduct of photosynthesis is oxygen. So these healthy plants, right, they add O2 to the water, and they provide habitat and food for other organisms. But now that algae on the top, those plants die due to lack of sunlight. So there's one. Number two, the algae is growing quickly and dying quickly. When it floats to the bottom, the bacteria start to eat it, and as the bacteria eat it, guess what it does? It consumes the oxygen out of the water, so it creates low oxygen zones, death zones. The fish that get trapped in there, they die. Again, these are called zones of hypoxia, dead zones, oxygen poor zones. So this is talking about pollution cleanup versus prevention. So once something gets out into the environment, you have to clean it up, right? And you're never going to get 100%, right? There's always going to be some left out there. So what's better, pollution cleanup or pollution prevention? Prevention, obviously. If you keep it from ever getting out into the environment in the first place, then you don't have to clean it up. Okay? So there's been a few FRQs in the past that have asked this, and they want you to respond with this. So if you ever have a question that does refer to, how can we deal with this pollution? You always want to say the best method, of course, is pollution prevention, and then come up with a plausible idea on how we could actually do this or implement some type of prevention system. Okay? Yeah, that's good. And that's the end of 20.2.